Alright, hello everyone, and welcome to my discussion section. So this will be taped because currently I am out of town, but for those who don't know, my name is Dahlia Pham, and I'm one of your teaching assistants for EAE 130A, and today I'll be giving you a brief introduction to OpenVSP and VSPAERO. So, what is OpenVSP, and what is the VSP project? I'll be going over that along with showing you the capabilities of this software, the theory, and everything you will need to know to get started. So, OpenVSP is an open source parametric aircraft geometry analysis and design tool. I'll try to say that again really fast. It's a very powerful, early stage aircraft design software. It's a good way to, quickly model geometries, and also has some analysis capabilities, with a built-in low fidelity aerodynamics tool called VSPAERO that can either run Vortex lattice method, which is VLM, or panel method analyses. I will definitely go over what these are. Propellers in VSPAERO are either modeled as actuator disks, as I mentioned last time in my last discussion about actuator disk theory, and the code that comes with it, or rotating blades. Though in this case, I believe you will not have to model them in OpenVSP because the code that Professor Chateau gave you should be sufficient enough to assess, the engines that you're using for this aircraft. So, where to download OpenVSP, I've included a link, and I will also put this in my I will put this on Canvas so that you'll be able to, click on things, and it can be run on Windows with a GUI or from a Cygwin command window if you're, into advanced tactics like what I do for work, for instance. I believe you can also run it on Mac. So if you have any questions on that, please feel free to reach out to me. I don't have a Mac, but the other TA, Carlos, does, so we kind of have that system going on. So, again, as I mentioned, OpenVSP is a powerful design tool. So, you can design very cool planes in it. Like, for example, this tilt rotor aircraft concept. So, you've heard a lot about urban air mobility, right? That's the next new hot thing in aeronautics. So, this is a tilt rotor aircraft designed for, urban air mobility or advanced air mobility. I believe we're trying to figure out which term to use, and this was designed at NASA Langley Research Center. Actually, during my internship, my mentor was the one working on this design, and you see this was completely built in OpenVSP, and I'll show you exactly why it's so easy to build geometries in OpenVSP. This is another aircraft. This is a Boeing 787-300 model. And again, this was modeled completely in OpenVSP. There are lots of capabilities where you can model ducts, fuselage, wings, and everything, and do a very, first stab analysis at it all. So I really like this software. And lastly, this is my senior design plane. So we did design everything in, OpenVSP, but we ported it off to SolidWorks to make it extra fancy. So with, some SolidWorks rendering techniques and all that stuff, this really looks like a professional plane. So I really urge you all this quarter, if you want to make a graphical representation of your plane, start with OpenVSP and then port it off to SolidWorks, and it will look professional. Like, this looks like something that VCs would throw money at. Sort of. Well, they kind of want something more alien spaceshipy, but you get my drift. So, another reason I'm going to campaign for OpenVSP is that these geometries for aircraft already exist for you and are low fidelity aerodynamics friendly. So the fuselage, the wing, it's already there. So you can use SolidWorks. Like, here, even the greatest SolidWorks modeler will be struggling when you try to model some of these curved surfaces in SolidWorks. After a week of work, this is what one of my friends produced, and it looks a bit, yeah. So you will definitely want to use this software instead of SolidWorks. In fact, I'm going to kind of show you how easy it is to build an OpenVSP model. So here in aircraft, the Boeing 737-800 is being built, by taking the aircraft's 3-view model from the airport planning manual as a reference in the background, and kind of using these geometry functions in OpenVSP to choose what component you want to model and alter the settings. So this brief video will give you kind of a gist of all of that. So you see they're taking the 3-view model and kind of sizing the key dimensions. You don't necessarily have to do this because I think they're already marked for you, but then you put that as your background in OpenVSP. And what this guy is going to do is he's going to split his screen so that he can work from different, models, but honestly, I just do it with one screen. And as you can see, now that he's put it all here, it's pretty easy to kind of model your geometry. So basically, modeling the aircraft in OpenVSP is pretty easy. When you first open up VSP, there's going to be this geometry browser that pops up, and you simply just have to choose something from this menu that you want to build, and each option has its own parameters to tweak around. So for the wing, you want to make sure you change your wing to the airfoil that you plan to use, and I can also show you how to do that at some point. Also, you can specify where in space you want this to be. So here is an example of just modeling the aircraft based on the 3 view models. So there's a fuselage, and you can see that they're matching it to the shape of the 3 view. Then there's the wing, and then the stabilizers are going to come in. For the wing, I can definitely show you a little bit about what parameters affect what. I don't know if I'll have enough time in this discussion per se, but if you reach out to me at any time, I'll be able to tell you kind of the important features of the wing to consider, because there's things like dihedral and everything that affect the wing's performance. So as you can see, yeah, I think video is just replaying itself, but when you have a canard, for instance, you'll have to model a wing kind of near the front of the aircraft, and you'll also have to I guess since it's a tailless geometry, a lot of the you won't really have to model like vertical stabilizers or horizontal stabilizers, but it's still good to kind of see how to do it. So there are lots of tools within OpenVSP. One of them, as you've just seen, is the aircraft geometry modeling. So this can be used to create the 3 view drawings of your configuration, which every aircraft needs. If you notice in every aircraft planning manual, you see the 3 view drawings. In fact, for those who are doing the NASA Design Challenge, that's one of the deliverables they'll always ask for. So it's important to do this, and I think that OpenVSP is a great, I think it is the software I recommend for doing this. You can definitely port it up to SolidWorks to take measurements, but I highly recommend this. Also, just wanted to mention, OpenVSP is dimensionless, so as long as you keep it all consistent, you can choose feet, meters, whatever. So you can build structures in OpenVSP too to port into structural analysis software like Patran. I've also linked, an example that someone did of this. So on my branch at the systems analysis branch, one of my interns works on kind of designing designs the models in OpenVSP, ports them to Patran, and kind of runs an analysis on the wing structure. So sometimes that can be really useful, because when you do these analyses, you'll want to have a model of the geometry. And modeling it in Patran, if you remember, and Peter Lee can tell you, is a bit of a pain, so it's pretty nice to have this. Another thing that OpenVSP has is a parasitic drag breakdown. So this can help you calculate your zero-lift drag breakdown, the components of your model. There are many different models that this software uses to calculate that, so make sure that you're familiar with the theory behind the calculations when you use it. I've made a link here because, Chateau will want you to back up every single claim that you make for this aircraft, and let's say if you just kind of select, I want to do a drag Torenbeek method, but what is Torenbeek method? What equations are driving this parameter? You're going to have to explain that in depth. And also, on that note, if any of you have questions on theory, please definitely email me and I will make sure to get back to you, because designing a plane is basically like setting forth all these proposals and having lots of evidence behind each of them. I could go on forever, but I'm running out of breath. So back to OpenVSP. You can also assign mass properties for weight. I think some of you have already figured that out, but it's pretty important for weight and balance, stability and controls. I've linked a tutorial here, and then obtaining aeropropulsive analysis and coefficients, such as the drag coefficient, lift coefficient, moment coefficients, and even thrust using VSPAERO. So thrust will be shown as the force in the x direction, as you know. And this is actually a great tool for, first level aerodynamic analyses, because, we don't always have time to run overflow or RAN CFD stuff, and this is pretty quick and pretty compact, and it gets us pretty close to it. Actually, even though I don't have it linked anywhere, my whole paper was, I published a paper with NASA Langley, and this is something that we did. We basically compared the results from OpenVSP from, the X57 wing for the drag, lift, and everything, and then plotted it against overflow and another software called Robin. And basically, it performed pretty well. I mean, the moments are a little bit difficult to predict, but lift and drag was good. Alright, so I guess I've been stating this a lot, but if you do use OpenVSP or VSPAERO analyses in this class, you will definitely have to defend the theory and discuss where these numbers come from, or else you'll lose a lot of points, and I don't want that to happen to anyone. So I guess one reason I was hesitant at first to introduce new tools to this class is because then you'll have to, defend the theory. But I think VSPAERO and OpenVSP has a ton of documentation on this. So, there are many reasons that a VSPAERO analysis may not be an accurate, statement. There could be issues with the mesh, because there is a mesh that auto-generates. There could be convergence problems, and etc. So, I kind of suggest it more as a tool to make up for capabilities the Fortran codes do not have, instead of, something you compare the Fortran codes against. You should compare your results from VSPAERO with what you get from Fortran codes, and they should be in some agreement. But I also think that this tool could mainly be used for visualization of the structural layout of the aircraft, and also, mass and inertial properties assigned to the components. But for aerodynamics, this comes from the heart here. Tread carefully, because VSPAERO's panel method code requires a lot of computing power and maintenance, and often you will get unrealistic results. So I really do recommend using the VLM setting, and I will definitely go into depth on what that is. So I'm going to give a quick demonstration of modeling in VSPAERO. But first, I'd like to explain some more theory. So, now this isn't really the question asked, but a lot of people always ask me, hey, why isn't CFD totally accurate? Well, you see, CFD software, let's go through what the differences are. CFD usually uses the full Navier-Stokes equations, usually Reynolds average Navier-Stokes equations, not direct Navier-Stokes, to solve aerodynamic loads on a geometry. This conserves mass, momentum, and energy. It is a high-fidelity method that is very computationally expensive. For example, running codes like overflow and star CCM plus require, using high-performance computing HPC facilities. If you use like a really rough mesh of some kind, that's not, suitable, because you're going to miss out capturing a lot of the phenomena that happens. So while you could run like, an ANSYS CFD simulation on your computer, on your aircraft, it won't be accurate most likely. So that's why a lot of people, when they look at early stage design, they don't use, CFD. This is very time consuming, and there are entire teams dedicated to kind of using this software. It can get hand wavy when you start making assumptions, because, why isn't CFD totally accurate? That's because, certain phenomena like turbulence modeling is a subject that's evaded many mathematicians, and people also have a hard time closing the Navier-Stokes equations. Actually, finding closure problems to the Navier-Stokes equations for specific conditions is one thing that people spend PhD theses doing. So I think that, for this class, it's very important to kind of start a little easier than that, because this isn't a CFD class and you could spend so much time on it. Like Vortex lattice method, on the other hand, it uses camber surface representation. So as you can see, this is like a degenerated representation. It kind of looks like a bunch of, planes. They're like flat and everything, but there is camber, so that's why it'd be important to specify your airfoil. But it uses this representation to solve linear, inviscid, and irrotational flows, which only conserve mass but generate solutions much faster. And then, how does this compare to wind tunnel testing? So CFD is not considered a replacement for wind tunnel testing or flight testing. They have a symbiotic relationship between the two. Of course, flight testing and wind tunnel testing is like king when it comes to all of this. But, at the same time, it takes a lot of power to run these wind tunnels. Like, have you guys ever seen the one at NASA Ames? It's like, I think the inlet is like the size of a football field. And imagine trying to run that. Like, your air conditioner costs money. Now imagine this inlet with the size of a football field. That's a lot of money. I think you spend like 100K per day or hour. Don't quote me on this. This is my personal guess. I do remember though one time I was in a CFD lab and they were talking about running wind tunnel experiments, and then they got hit with a quote for that, and then we're like, oh no, we're not going to do that. We're going to put a scale model and go look for a cheaper wind tunnel. So again, that's kind of the theory. So before I launch into how to do Vortex lattice method in OpenVSP, I know that theory might not be the most fun, but you definitely need to know it before using these tools. And I'm going to give you kind of a case study of my foolishness as an undergrad. So when I was an undergrad, I wanted to start using CFD tools right away because that's what looked the coolest. Plus, people in the industry did it, and, that's kind of what venture capitalists throw money at, these very colorful, cool pictures. And I was like, whoa, because, I wanted to be an aerodynamicist. But for senior design, you won't really need CFD, and it wouldn't apply. So, because I was foolish and tried it, I'm going to tell you exactly what problems I ran into. Mesh resolution. This can take months. The bulk of most studies for CFD is just trying to find a good mesh for whatever you're trying to model. And this can take months. This can even be a paper. And let me just tell you, I could not figure that out for the life of me. Like, I'd get results, I'd show them, my professor would be like, okay, what does this mean? And I was like, help me, I don't know. And then computational power. So then I was like, okay, I can't do the whole 3D aircraft. So what if I take a 2D cut of the wing and generate a mesh around it, like a C-grid? And I'm pretty sure if you see my YouTube channel, you can see a tutorial I made of that, because I did get some results, but it was a NACA 12 airfoil, which is not going to be as complex as, what airfoil you're going to choose. But I even used the HPC1 cluster, and boy, it was a pain. So when you do CFD at work, how do people do it? So I reached out to a friend, and they usually tell you what settings to run, and usually have a mesh that's given to you. And you don't have to build things from scratch. So imagine trying to do this on an undergraduate plane in 10 weeks. You will get results that CFD experts who built the codes from scratch, like, Professor Chateau, will question you in depth and think it's sloppy engineering. They'll be like, did you just hand wave a lot of this? And you're going to look at them and you're like, oh, I don't really know. So for the aerodynamicists out there, especially the ones that, really want to do this, I promise you, just learn Prandtl lifting line code, Xfoil, MZs, and Vortex lattice method. That is more than enough. Now, as you saw, I mentioned something called panel method. I'm sure you're kind of familiar with panel method from Professor Robinson's class. Basically, it gets the CP distribution on this 3D geometry, and from that you can back calculate the lift and drag. I do not recommend using panel method because, I work on the VSPAERO software, and there's still a lot of stuff that's not great with it. Like, when you get your CP distributions, you'll start seeing, a wild range of CP, and you're like, how did this happen? Well, it's because right now panel method is not the best way. There is a software that, people had to use last year called FlightStream. And again, I also worked with the developer of this. His name is Vivek, really nice guy. That software cannot run things like, rotating blades. So you'd have to use an actuator disk, and also it's just, it takes a lot of time. So Vortex lattice method should be enough. So what is the theory behind VLM? VLM models lifting surfaces, such as wings of an aircraft, as infinitely thin sheets of discrete vortices, independent of thickness and viscosity. So what VLM does is it simulates the flow field of a geometry with the pressure distribution around the body, or sometimes the velocity. Velocity and pressure kind of go hand in hand. This is used to obtain the induced drag and lift, which is also seen in, panel method, except, that takes into account thickness. Vortex lattice method does not. It is basically an extension of Prandtl's lifting line theory. You're all familiar with that in the code, where in lifting line theory, the wing of an aircraft is modeled by a single horseshoe vortex. VLM is different from LLT because it uses a lattice of horseshoe vortices. Okay, so you can see on this model, there is tessellation. How do you control the tessellation of your mesh? Well, that is a parameter in the geometry browser. So you'd have to go over here and kind of muck around with those settings. I gotta keep dragging it onto my other monitor. There we go. It's been a hard quarter, everyone. And as you can see, there are lots of different parameters. The parameter that controls the mesh fineness is this one, called tessellation. And, for the fuselage, I believe it's not, you'll want to have pretty fine tessellation around the front and the back. And for the wing, that's the most important part. You'll want to mess around with that too. So I guess when you first do modeling of this, kind of make your mesh fine, but not too fine, because that does drive your how long your computation takes. And I can go into the specifics of this. Right now, I think if you use default settings, it should be fine. And if you see any singularity points, that will be appearing in the analysis. So, anyhow, back to vortex lattice method theory. It uses a lot of horseshoe vortexes. It's not just one. So what are the assumptions of VLM? So the flow field is incompressible, inviscid, and irrotational. When you start taking EAE 126, you'll get a better idea of what this means. But basically, these conservative assumptions aren't actually as conservative as, mass, momentum, energy, and all that stuff in the Navier-Stokes equations. It's like a very simplified flow field. So the lifting surfaces, as you can see, are thin. The influence of thickness on the aerodynamic forces is neglected. See, what makes VLM different from panel method, for instance, is that the lifting surfaces have a thickness for panel method. And not in this case, but the camber is still factored in. And also, the angle of attack and angle of side slip, oh, there's a typo, side slip are both small angle approximation. So that kind of goes into, the theory and derivation of these equations. I'm going to spare you a lot of the equations that are used, but basically, all the lifting surfaces of an aircraft are divided into some number of quadrilateral panels, and a horseshoe vortex and a collocation point. Oh, I'm going to jump back a little bit. Just to be clear, this picture depicts lifting line theory, and this is panel method. Look, there's like a pretty little mesh here. Okay, now that I've covered that base, back to the VLM equations. So all of them are divided into a number of quadrilateral panels, as you saw in that picture, and a horseshoe vortex and a collocation point, or control point, are placed on each panel. So the free stream velocity vector is given in terms of the free stream speed. So this is the velocity vector. That's the free stream speed. You need to kind of figure out what that is based on what conditions you're flying your aircraft. And alpha is the angle of attack. You're all familiar with that. Beta is a side slip angle. You'll become familiar with that in stability and controls, but not here. Sometimes we like to pretend that beta is 0 because, if beta equals 0, that means your flight is symmetric. Like you're in steady flight. So what do we do next with these equations? So flow tangency is a condition, and it's applied via the Newman boundary conditions to each collocation point. Wow, that's a lot of jargon. Basically, what we're saying is that the flow is tangential. This is imposed by saying, the normal velocity across the camber surface is 0, because that's what we need to start this analysis. This is essentially the equation that tells you that. You can look up kind of n is number of panels, of course. W is another factor that will we can discuss in depth later, but the most important part is the horseshoe strength, and n is normal. So, the dot products of these equations result in the following matrix, where B is determined by the free stream speed and angle of attack and side slip angle, as you can see here. And look at this. You have your typical matrix, AX equals B. And of course you solve for X. And in this case, X is the matrix of the horseshoe vortice strengths. So I'm sure you can use numerical methods on this. Again, this is probably a call to Engineering 180, but this system of equations is solved for gamma, which is the horseshoe vortex strength, and this is used to find total force and moment vectors around the origin, and it takes into account all the horseshoe vortices on that surface. So finally, what are we looking for? We're looking for the lift and induced drag, and that is obtained from the forces in the x, y, and z direction and the angle of attack. So in these cases, we assume that the side slip angle is negligible. So if beta equals 0, that implies symmetric flight, and then bam, we get these equations. So that is essentially the theory behind VLM. If you have any questions on this, please feel free to email me, and also I can direct you to some papers, like the papers where I got some of this information. How can you use Vortex lattice method? So let me kind of drag everything back onto this screen. First, what you'll have to do is create a degenerate geometry of your structure. So what you want to do is hit execute on this, and it will make a degenerate geometry of your aircraft. And if you want to preview that later, there is an option in the GUI to do so. So now that you have that done, I also like to hit save. You can open up the VSPAERO console. So what you can do is you can run kind of a batch analysis of angles of attack and also what your Reynolds number is. Just for, purposes, I'm just going to keep this fairly simple, 3, and I'm going to use Vortex lattice method. If you want to look at the VLM geometry, this is the degenerated geometry you created. It's all kind of like planes. And by the way, this model is an Embraer 175 model I was working on. So as you can see, it was modeled from the aircraft planning manual. So now that you have that set up, you can look at all the settings, make sure you select from the model. You can calculate the CG, but I haven't done anything with the mass properties here. So of course you'd have to set it whatever it is. Just for curiosity, let me see what it is here. Okay, well, it's a little bit interesting. I don't know if it's right, but that's something you'll have to check. Make sure that you have the Carmen-Cien Mach correction. There's more on that, and number of CPUs. You can go up to I think 8. And also, these are probably the settings you want to use. I'm actually going to show you something pretty cool. So I'm going to launch Solver just to initialize, and then I'm going to kill it. So, Dahlia, why did you do that? Well, now if you look in your downloads folder or wherever you have your geometry, there's a bunch of stuff here. Okay, what is that? Well, your history file, no, I don't want to, shows the computations of the force coefficients, right? And I guess if you want to initialize it again, because there's a file I'm looking for, gonna let it run again. Gonna kill the solver early. All right, where is that file? There it is, the VSPAERO file. So as you can see, this is another place where you can change your inputs and outputs, and it kind of prints out like this. And you would run it like a similar code to what Professor Chateau has. If you use Cygwin, this is what you'll mostly be working on. The .vspaero file is full of the initial conditions. But if you use the GUI entirely, let me show you how that will be like. So we're gonna have to it'll automatically reset once I hit it again. So these are all the settings we want. Okay, now we can hit, launch solver. And we're gonna let it run. You can also set the wake iterations based on what you think will give you accurate results. This shouldn't take too long. It does take some time, especially when you have a finer mesh. So let's wait on it. All right. So now is the fun part. You get all these results. So as you can see, this is kind of like the plot of the span, and kind of, let's see if you can find the lift distribution. This is exactly what you would expect for the aircraft, and I think you remember how to use, how to get lift distributions. And you can look at the convergence. Convergence, it was not that many runs, but I think it stays. This is about all right. You can check the different parameters. The most important ones, of course, are CDI. Not too good, but these two are good, and because this one is for angle of attack of 15. So as you can see, it didn't really converge that much. What's important is you look at the CDI, and you're like, okay, for 1 and 8 looks good. For CL, as you can see, not so great for angle of attack of 15, so your results may be spotty, but in this case, I didn't set the wake iterations too high. Sometimes I set them up to 16. But this kind of gives you an idea of, the quality of your results and kind of how the distribution looks, and if there's anything you can do to kind of muck with it. So now there's another window you can use, launch viewer. All right, so here's your degenerated model, and you want to kind of show the pressures, because the pressures will tell you a lot. Let's also set the scale for them. So run label so you know what it is. Contour legend. Okay, this is a fairly good range of CPs. See, if it was really, really bad, these CPs would be very weird numbers and very far away from each other, and then you know that, hey, I need to increase the fineness of my mesh. So looking at the different solutions, still looks good. As you can see, there is a weird point here, negative 4.36. That means, somewhere along the line, we have to kind of make our mesh finer. And, for some of these simulations, it's okay to just do the fuselage and wing, because then you can just add everything in the back as, additional drag or flat plate area. You can just do the fuselage and wing. I think that's the most important. Actually, you can just run the wing by itself, and that will tell you plenty about the aircraft. And also be more accurate. And then if you look here, yeah, the ranges aren't great. So I would say I can't really use angle of attack of 15 for any information, but if you look at the other values, at angle of attack of 0 or 1, looks pretty good. Alright, so now you have a ton of information. What do you do with it? Well, you can export these results to a CSV file. I'm going to call it example. And let's see how that looks. Alright, so example. Alright, so here's our history. And basically it shows you what the calculated lift, drag, and everything is. But you know what? This is a lot of information. So this isn't usually where I go for it. What I do is I look for this one file called polar. Okay, polar files. And the .polar files will output it as this. This is what the final iteration calculated for the CL, the CD, and CDI and everything. So we're going to disregard this data point because we already know the results are not, fantastic. But basically what this tells us is you can build your alpha versus CL curve here. You can get your drag polar from here. I don't really trust the CD naught from here, so I mostly only use the CDI, and then I take the CD naught from the parasitic drag tool, which I'll also show you how you get, and you can get L over D. So basically, similar to what you do before, you create a MATLAB script that can read these files, convert it to a .text file, and then plot angle of attack versus CL. You can use MATLAB for it, and right now I don't have a script for you guys, but I'm sure it should be really easy. So that's kind of what VSPAERO tells you. And let me see if they have something else. Let me see. All right. Okay, yeah, they have, you can preview your plots. There we go, that's exactly what I was looking for. So let's put alpha on here and then CL on the y-axis. And as you can see, predictably, it continues to increase with increasing angle of attack. Now, you also have to consider that, aircraft stall. And angle of attack of 15 is pretty high, so you would expect that it would stall, but because there's a lot of assumptions being made, stall isn't well predicted by these methods. So you have to keep that in mind. There is a way to simulate stall, for instance, but I think it does require working with the GUI instead of a flag that you can easily turn on and off. But in this case, I don't think you'll be primarily getting your CL curve from OpenVSP. I think this is just a good visualization and gives you an idea when you compare your numbers. And then alpha versus CDI. Of course, as your lift increases, there is more induced drag from it. And you can take a look at other parameters too. I think it's pretty handy, and in the future, if you don't use it for this class, this is a very good first order tool. So now that I've mentioned the parasitic drag tool, I will also show you how that is done. Alright, so I'm going to do a quick overview of how to use the parasitic drag tool. I'm not entirely sure if you will be using it in particular for this class, but I think it'd be a good thing to go over. So let me open up VSP right now and then look for the folder I have, or rather the file. This is for the Embraer 175 that I made, and here you go. This is the Embraer 175 built from the aircraft manual. So from here it's like, how do you get the parasitic drag? Okay, I just remembered. You hit Alt and then you drag it, then with your mouse, then you can drag it. So as you can see, this has a fuselage, wing, horizontal tail, and vertical tail. So let's say, for instance, I want to do a parasitic drag analysis. So as you can see, there are lots of parameters to play around with. First off, you're going to have to kind of choose which skin friction equation you're using, because right now these models are pretty reliant on the skin friction. And see, there are a lot of different ones for turbulent skin friction. But for now, I'm not going to go into that right now. You'll have to grab your reference area from the model, and then there are many ways to calculate the CD naught. So there are all these methods. So it's like, what do I do? You also want to make sure that you look at all these settings and set it to the right one. And to calculate the CD naught, that's how you would do it. So what exactly do you do? Because you can't just pick a form-fitting equation and be like, this is what I used, without explaining it, because, Professor Chateau, he definitely cares deeply about the theory and your understanding of it. So where do you go for that? Where do I go for that? I go to the documentation for OpenVSP. So here it describes all the different ways that this is computed, like, with flat plate area and everything, and it kind of tells you what everything is. And I guess based on the assumptions and your kind of research into it, you would decide, okay, that works for my application. So right now, you'll have to take a look into that. There's DATCOM, that's one method. Crew, he's a Stanford professor. I think he's still around. Tornbeek is the most popular one. That's the one that we used because back in the day when we were doing this for our senior design project, Tornbeek was one of the required readings, I think, or an optional one. So there are lots of different equations to describe, the form of whatever you're computing the drag of. And as you can see, they all vary. So in this case, I'm going to show you, let's say, make sure you keep all of these constant, but let's do Tornbeek. That's one that I know well. And from that, we hit calculate the CD naught, and there it is. And you'll want to, click on the wetted area because that's how much surface area is being exposed and thus relevant. So make sure you select this. Select all the components too. Actually, I'm not sure why it toggles like that. Let's see. I guess it doesn't vary too much. See, there are things that I'm still learning. What I'm gonna go with is the wetted area because that's what I'm familiar with. And here you have a weight breakdown. What happens when you toggle this? Lots of mysterious things happening. Oh, I see. These two get switched around for some reason. I guess, maybe it's alphabetic order. See, maybe it helps for you guys to see me figure this out too. So Doesn't matter what you select, but this will give you a weight breakdown. So see, you have the CD for each component, the total CD, and this one is going to be, I guess that's 211 drag counts, but this is a pretty good approximate tool. And now you know how to use that. And as usual, thanks for coming to this discussion, albeit online. I put in the video where to skip to if you just want to get that information because, I was a student once and sometimes I just want to see the demo. And I go back and look at the theory when I have to. That's not a great practice, but, I'm sympathetic. So I like to close off my discussions with a plane of the day because I am an airplane fan outside of class, which is kind of sad. You're like, what do you do with your life? Well, I like to read airplane news. I also like to garden. I also like to play video games and, watch shows. So I do have a bit of a life. But, a lot of my life I do spend on airplanes. So, the plane of the day. The Airbus 320neo is one of the best-selling aircraft on the market. It was launched in 2010 to take on a new generation of single-aisle jetliners, and it comes with a lot of interesting design features that contribute to its success. God, I sound like a salesman for OpenVSP and this plane. But you know what? Let's continue. This plane has a maximum Mach operating limit of Mach 0.82, looking like it kind of dabs a little bit in the transonic region, and features blended winglets called sharklets and uses either the Pratt & Whitney 1000G engine or the LEAP 1A engine. So this re-engining, with more modern engines, leads to lower emissions, less fuel, and less noise compared to its competitors, which are very old, if I can just diss another airplane real fast. This is kind of like the creme de la creme of commercial airliners these days. So I think everyone should know it exists because this stuff is the future. And also, just knowing what planes are in your airspace really changes the game for you because then you start looking around, hey, how is it designed? And how can I design an aircraft like that? So, because I'm an aerodynamics fan, let's just briefly touch on sharklets. So winglets or sharklets are upward or downward curved extensions at the wingtips. So this comes with a weight and drag penalty, but winglets improve the environmental performance of an aircraft by reducing the induced drag caused by lift, thus minimizing fuel consumption. Okay, what's another way to do this? You can extend the wingspan, but if you're limited to a certain wingspan by design requirements, it's a lot of load, and also in this class, there's the wingspan, I believe, is set to 36 meters for the plane that you guys have to design, or, hangar width, which is really important. You want to go in the door. So when you're facing these challenges, winglets really are the way to go. And, they're inspired by flight, like how birds fly. And I really like winglets. A lot of stuff goes into them. And as you know, a lot of airplanes is inspired by aviary. Okay, what do you say for birds? Okay, birds. Birds, bats, everything. People, analyze that to death, but winglets are something that we gleaned from, birds, even swimming creatures, and these sharklets on the Airbus 320neo were designed by Airbus engineers. So, if you ever wondered, hey, what do aerodynamicists do? They do cool stuff like this. So, this is the Boeing 737 MAX's biggest competitor, and that one has some doubt in the industry because of the many crashes it had and MCAS. But, this is the one that people are looking to because, it's an efficient and widely used airliner. So aircraft designers who work in civil aviation should definitely take notes. And I'm sure that there's a lot of things that Airbus won't tell us because it's so successful. I think even 6 days ago, this aircraft recently sold over 770 gross orders valued at $45.9 billion during the pandemic. And wide-body airliners are kind of going slow, but I am really not the best at reading out loud, but, I'll get better at it. And thank you for watching this, even though there wasn't a formal discussion. We'll be in person soon, so you'll be able to kind of see me flounder in person. But wide-body airliners, the big planes with lots of aisles, those are kind of going slow because people aren't traveling these days because of the pandemic. But single aisle jetliners, they're still going strong and they're really efficient, in terms of drag too. Even the front cross section of the fuselage is a lot, the diameter is a lot smaller than, the wide ones, I think. And if I'm wrong, I'm sorry. Okay. I decided I'm not going to do another take. So again, if you have any questions or concerns, please feel free to email me. Some of you even hit me up on Discord, and I really appreciate that. And some of you are really on top of it, like just utilizing office hours and everything in spite of, what's going on with this class and everything else during the pandemic. So I just want to take some time to say I really appreciate that and think that you guys are a great class. And thank you so much for watching this video and getting to this part. Please let me know if there's any way that I can help with the software or anything. And if you find any bugs, that's part of my day-to-day job apart from TAing this class. So just hit me up and let me know. And from there on, also feel free to send me any kind of feedback. So this is my first time TAing, and I really enjoy it, but I think first and foremost, I want to make sure you guys enjoy it. So, of course, tell me ways I can improve. I think my mic might be close to my mouth, so I'm sorry if you guys have to put up with my loud voice. And I'm trying to get a better presenter voice, because otherwise I kind of just blurt things out. So again, let me know. I'm always learning, and thank you so much for coming to discussion today. Hope you all have a great day.